One of the biggest challenges in modern technology, the thing that's really holding us back, is heat. Our gadgets, our engines, they just keep getting more powerful, and because of that, they get hotter. So, how do we stop everything from basically melting? Well, the answer might just be a revolutionary new material that could supercool our entire world.
All right, let's just jump right in. This problem is way bigger than just your phone feeling a little warm in your pocket. We're talking about everything from high-performance car engines to these massive, sprawling data centers. Managing heat is one of the toughest nuts for engineers to crack. You see, better cooling means better performance, and right now we are really starting to hit a wall.
So why is this so important? Why do these high-performance machines have to keep their cool? Well, it's a pretty simple question, but the answer is a little complex. Every single watt of power that your computer or your car's engine uses generates waste heat. And if you can't get that heat away from the components fast enough, what happens? Performance tanks, the parts start to break down, and eventually things just fail. And our constant push for more speed and smaller gadgets just makes the whole problem that much worse.
So how do we deal with this right now? Well, most engine coolants, the antifreeze in your car, are a mix of water and ethylene glycol. And water is amazing at moving heat. You can see its thermal conductivity here is a pretty solid 0.6. But we have to add ethylene glycol to stop it from freezing solid in the winter. And here's the real catch. Ethylene glycol is an absolutely terrible conductor of heat. Look at that number. It's less than half as good as water. So get this, we are intentionally making our coolant worse at cooling just so it can handle cold weather. That's a huge trade-off.
This is where the science starts to get really, really cool. If our base liquid has this built-in performance limit, what if you could just upgrade the liquid itself? That's the whole idea behind nanofluids, and it's a new frontier in managing heat that has researchers incredibly excited.
Okay, so what in the world is a nanofluid? It's actually a deceptively simple idea. You take a normal liquid, like water or antifreeze, and you mix in a tiny, tiny amount of incredibly small, specially engineered particles. And when I say small, I mean particles that are less than 100 nanometers in size. The whole goal is to give the liquid these new super properties without really changing what it is.
And this right here is what we're talking about. This isn't just like mixing sand into water. This image, taken with a scanning electron microscope, shows you the incredible, paper-thin, almost sheet-like structure of these nanoparticles. They're designed from the ground up to interact with the liquid on a molecular level. It's pretty amazing stuff.
So how does this actually work? Here's a good way to think about it. Imagine heat moving through a liquid is kind of like a bucket brigade passing buckets of water down a line. The liquid molecules are the people in the line. Now, by adding these nanoparticles, you're basically dropping a team of super-fast, hyper-efficient little helpers into that line, which lets them pass the heat buckets along much, much faster. So if you're going to add a super-fast helper to your liquid, which one do you pick? There are a bunch of options out there, but scientists are really zeroing in on one that seems almost custom-made for the job: graphene oxide. Let's dig into why this stuff is such a potential game-changer.
And this right here, this is why. Just look at these numbers. Water, our good old baseline, is sitting at around 0.6. Silver, which we all know is a great conductor of heat and electricity, is at 429. And then you have graphene. At around 5,000 watts per meter Kelvin, its ability to conduct heat isn't just a little bit better, it's in a completely different universe. It is one of the most thermally conductive materials ever discovered. Period.
Now, you might be thinking a wonder material like this must be super rare or impossible to make. But actually, the process starts with simple graphite powder. Yeah, the same stuff that's in a pencil. They use a well-known chemical process. It's called Hummer's method, that uses some strong acids to carefully peel the graphite layers apart and then oxidize them. And what you get is graphene oxide, which has this one crucial property. It loves to mix with water. That makes it absolutely perfect for creating a stable nanofluid.
Okay, so the theory is mind-blowing, right? A superconductive material made from cheap graphite that you can just mix into water. But does it actually work in the real world? To find out, researchers had to put this new graphene oxide nanofluid to the test.
And they didn't just, boil some water on a stove. They used this highly precise technique called the 3-omega hot wire method. Try to picture a metal wire that's thinner than a human hair, submerged in the liquid. They run an electric current through it, which makes it heat up just a tiny bit. But here's the cool part. That same wire acts as an ultra-sensitive thermometer. By measuring exactly how fast the liquid pulls heat away from that wire, they can calculate its thermal conductivity with incredible accuracy. It's like watching the coolant work in real time on a microscopic scale.
And here are the actual nanofluids that they tested. Over on the left, you've got the base fluid, totally clear. As they add more and more graphene oxide, you can see the liquid gets darker. But just look at those concentrations. We are talking about minuscule amounts. The darkest sample on the far right has just a little over 1.5% of the additive. That's it.
So let's look at the raw data. The base fluid starts off at 0.59. You add just 1/3% of graphene oxide, and boom, it jumps to 0.69. By the time you get to a 1.25% concentration, the thermal conductivity has hit 1.00. That's not just a small bump, that's a massive leap in performance.
And if that table of numbers wasn't clear enough, this chart makes the result absolutely impossible to ignore. That blue line shows the actual experimental results, and you can see it's not some gentle little curve, it's a steep, almost exponential takeoff. The more graphene oxide you add, the more dramatically the fluid's ability to cool just skyrockets.
So, here's the single most important number to take away from all this. With just a 1.25% concentration of these graphene oxide nanoparticles, the researchers measured a 70% increase in the fluid's thermal conductivity. Let that sink in. That's not a minor adjustment. That is a fundamental breakthrough in the ability to transfer heat.
A 70% improvement in a lab is, well, it's incredible. But for this to actually change the world, it has to be practical. So what are the real-world implications here? What's the bottom line?
And of course, here we have the classic trade-off you see with almost any new technology. On the one hand, the performance gain is just undeniable. You can radically improve existing coolants with just a tiny pinch of this stuff. But on the other hand, making high-quality graphene oxide nanoplates at a massive industrial scale is still really, really expensive.
But if, and it's a big if, that cost comes down, this technology matters to basically everyone. It could mean car engines that run more efficiently and use less fuel. It could mean laptops and phones that can run way faster without overheating. It could mean electronics that last longer because they aren't constantly being baked by their own heat. We're talking about unlocking the next level of performance in the tech we use every single day.
So what's the big takeaway here? Our technology is fighting a constant war against the heat it creates. And our old weapons, our traditional coolants, are hitting their limits. The potential solution? These new nanofluids, specifically a normal liquid spiked with a tiny bit of graphene oxide. And the result is a potential supercoolant with a staggering 70% boost in its ability to fight that heat. Now, cost is the major hurdle, for sure, but this research blows the door wide open to a future of more powerful, more efficient, and longer-lasting technology. So the question really isn't if we need a cool down, but whether the price of this revolutionary one will drop fast enough to meet our ever-heating demand.